last video ended with us properly learning the syntax for defining a function in Mathematica, and we were able to teach Mathematica about our sequence a sub n. We were then able to combine built-in functions in Mathematica, like the table function, with the new function that we had defined seamlessly in this input line right here. What I'd like to do next is continue on with investigating this sequence a sub n and also define a sequence s of n of nth partial sums of the terms of a of n, so we can start answering those questions we had about this particular series, such as, is this series geometric, and what do we think those partial sums are converging to? So let's begin by showing that this sequence does not form a geometric sequence, and therefore we do not have a geometric series. Now, recall that a geometric series is one that has a constant ratio by which we multiply each term in the sequence to obtain the next term in the sequence. We can therefore ask Mathematica to create a table for us of values, and what we want that table of values to be is the ratio of this term to this term, the ratio of this term to this term, or the ratio of this term to this term, the ratio of the nth plus first term to the nth term. And we can do that as n goes from 1 to as many as we'd like. Let's do 5 here. And when we ask Mathematica for that table, it shows us that the first multiplier is a third, the second multiplier would be a half, the third multiplier would be 3/5, then 2/3, then 5/7. These numbers are not all the same, meaning that we are not obtaining the next term in the series by multiplying by the same number over and over again for each term in the sequence. So something like this justifies for us that this is not a geometric series that we're dealing with. Again, if it were a geometric series, all of these numbers would be the same. So this is not a geometric series, but we can still create a table of values of the sequence terms and the partial sums of the series, and we can investigate the limit of the sequence of partial sums to see if it's clear whether or not that's converging. But in order to do that, we're going to have to define the sequence of partial sums. So let's call that term s of n, and we know now that we need to place an underscore after the variable n, and we need to use a colon equal in making this definition. And notice that the formatting has already changed. The n has become italicized. It's changed colors to that greenish teal color, and so Mathematica understands what we're trying to do here. Now, the way that we define a sequence of partial sums is as a sum. So I'd like that great sigma notation that we've been using on pencil and paper. It doesn't show up in the basic version of this math palette, but it shows up in the advanced portion of the basic math assistant. Here we see that sigma. And Mathematica even puts words in each of these spaces telling us what goes where. So the first thing we need is an index. I'm going to use the letter I for that. We then need to know where to start. Our series starts at 1, and because we're looking at the sequence of nth partial sums, we stop summing when we've reached the n value that the user inputs into this sequence. Now, what is it that we're adding? We are adding the addends. And so what we want to do is call our built-in sequence A, evaluated on this value I, the thing that's changing here, so that we will ask Mathematica for a of 1 plus a of 2 plus a of 3, stopping ultimately at a of n, when n is telling us we're at the nth term the nth partial sum. So we go ahead and make this definition for Mathematica, and then if we'd like, we could ask Mathematica for a table of S of n values as n goes from 1 to, say, 5. We hit enter, and Mathematica gives us some values. Before we go on, let's do a sanity check to make sure that we think that these values are correct and appropriate. Up here, we know the values of a of n. As we've seen before, the first partial sum is always equal to the first addend, and we do have those things matching up right here. The second partial sum should be the sum of 1/2 and 1/6. So to double check that Mathematica has done this correctly, we could ask it for 1/2 plus 1/6, and it does give us 2/3. The third term in the sum should be equal to 1/2 plus 1/6 plus 1/12. Again, we can check, and we get 3/4. So it appears that this table is giving us correct values. Last but not least, I'd like to show you a way that we can have Mathematica print these values and these values right next to each other so that we don't have to go up and down with all of these definitions in between. Let's say we wanted Mathematica to give us a table of a of n values followed by s of n values. And we want our n to range from 1 to 5. This syntax will result in an error. Mathematica doesn't like that we have more than 2 things passed into the function. So what Mathematica wants us to do is group the things we want listed with braces right here. And if I now ask Mathematica to do that, it shows me a sub 1, s sub 1, a sub 2, s sub 2, a sub 3, s sub 3 in this way. We could take this one step further if we wanted and come up here and add an n to the mix. So we know that this is a1, a2, a3, a4, a5. And if we wanted to get really fancy and have Mathematica show it to us in a table like what was shown in our slides, we could ask Mathematica to show us the transpose of this table and have it do that in matrix form. And here we are. This row is the n's, this row is the a sub n's, and this row is the s sub n's. Now once we see these s sub n's, it should be clear to us that there's a pattern going on expressing what the value for s sub n is. So even though this series is not a geometric series, by getting some values for it and filling in a table of n's, a sub n's, and s sub n's, we're able to see a pattern in the s sub n's and formulate what we think the limit of this series might be from this pattern. But the last question we haven't understood is why the sum of these numbers in particular is giving us such a nice formula for what the s sub n value is. And that will be the subject of our next couple of videos.